Good afternoon, everyone. Welcome to this PE coaching session. In today's session, I will give you a simplified overview about hydrocarbon saturation evaluation for non-petrophysicists. I see some of the petrophysicists joining this session. They might find it boring, but your role will be also supporting me to add to the session. I'm targeting non-petrophysicists for this session. First, I will start with a quick overview about myself. My name is Mona. I am a senior petrophysicist, currently working in Bahjarima cluster. This is not my first coaching and knowledge sharing session. Over the past 3 years, I have delivered several coaching and knowledge sharing sessions. I enjoy simplifying petrophysical concepts and make them easier to understand. And today I will be sharing a simplified side on hydrocarbon saturation evaluation. So the level of today's session will be very basic. This slide summarizes what I hope to achieve from today's session. First, I will start with very basic definitions. I will explain what is fluid saturation and what does saturation evaluation really means. Then I will take you through the story of the reservoir, starting from the rock deposition to hydrocarbon migration to fill the reservoir. And finally, I will give you a high-level overview of the main methods used to evaluate the hydrocarbon saturation, focusing on the most common methods we use in PDO from both logs and core. I'd prefer to keep the questions until the end of the session to help you digest the flow of the presentation. Before I go deep on the session topic, let's start with a simple challenge. Here you see a glass of water with oil floating on the top. I designed this challenge to make you think like a petrophysicist, without equations and without logs. So because we are meeting virtually, your task is not to measure the amount of oil in this glass. I don't need that information from you. Actually, I can tell you what's the amount of oil here. It's 50 ml. The volume is 50 ml. I don't need that from you. Instead, I will show you 3 different measuring methods that could be used to measure the amount of oil in this glass. And your task will be simply to observe each method, and you will need to rate each method on 3 best, I call them winning conditions. You will understand later why. So the best method should be accurate, should be doable, how easy to apply it, and not costly. Or you will do this ranking while watching the videos. After each method, I will show you the measured oil volume for comparison. So I will start with the first method. This method, I call it the spoon method. In this method, I want you to watch how the oil volume is measured. A spoon is used, as you can see from this video, to transfer the oil from the glass into a small cup with a non-volume capacity of 50 ml. I want you to watch this video, and I want you to focus while watching this video on the effort required to measure the amount of oil, and think of any issues or problems for using this method that might not make it the best for measuring the amount of oil. At the end of the video, I will ask you to do the rating, and I will take you through that. So let's see. Imagine if your work is to do this task every day. Keep observing. You can see there is spilled oil on the table. And this is the total measured amount of oil in the cup. The amount should be 50 ml, and the capacity of this small cup is 50 ml, but it doesn't fill it. So now I will ask you to start rating this method. I want you to write on the chat box, and then I will read your responses. What do you think about the accuracy of this method for measuring the oil volume? You can write on the chat box. What do you think? Do you think it's accurate or not accurate? Can you write your responses on the chat box? Semi-accurate, Ahmed. Not accurate, Fatma. Just we will take them one by one. We start with the accuracy. We will go later on the other options. Not accurate, Nihal. Maisa, not accurate, not accurate. Medium accuracy, man. Not accurate. Florence, yeah. So now let's rate it based on the doability. Layan, not accurate. What do you think about doability? Is it doable or not doable? If I ask you to do this exercise on daily basis, would you think it's doable for the long term? What do you think? I want to hear your views. What do you think about the doability? Fatima, not doable. Rahma, not doable. Aisha, not doable. Yeah, not doable, not doable. Kifah, I will give you this work. I will let you do this duty. Doable, yeah. Kifah, rating it as doable. Doable but not accurate. Khalid, Alawi. Okay, yeah. This is the idea of rating different methods. Now I will take you, it's tedious, Florence, exactly. So not doable for routine, exactly. Now let's take your rating for this method as cost. And when I say here cost, I'm talking about the cost of this small cup and spoon for this case. Do you think it's cheap, expensive? What do you think? Cheap, Fatima? Cheap, yes, cheap, good. Florence, Layan, cheap, yes. Yeah, majority of you thinking, rating it as cheap. Yeah, so exactly. So you can see in this method, although it works, but still have some problems that make it not accurate, not doable, although it is cheap. This method is messy, slow, not accurate, requires many scoops, some oil is spilled, and some oil mixes with water, and the measured amount of oil here from this method is 30 ml. Remember, the exact number is not the focus right now. What matters now is evaluating the method. This is the main topic of today's session. Now I will take you to the second method. We will repeat the same exercise for method number 2. This method, I'm using a volumetric tube to transfer the oil from the cup, from the glass into the small cup with a non-volume capacity of 50 ml. Again, I want you to watch the effort required to measure the amount of oil and think of any issues or problems of using this method that might not make it the best. After finishing this measurement, I will ask you to do the rating exercise again. Imagine if we have to measure the oil underground using this method. This time, no spill of oil on the table. It's more cleaner method. But I want you to think of if there is any issues as well that will make you rate it as accurate or doable or in terms of cost. Yeah. Now get ready. This is the total amount of the oil transferred into the small cup of a capacity of 50 ml. And there is still remaining oil on the glass. Now let's rate this method in terms of accuracy. What do you think? Accurate or not accurate? Fatma, not accurate. Any more responses? Maisa, not accurate. Florence, not accurate. Layan, not accurate. Ryan, not accurate. Majority thinking it's not accurate. Athir, not accurate. I agree. Now let's rank it, rate it for the doability. Is it doable or not doable? If you need to do this exercise on daily basis, what do you think? Doable or not doable? Not doable. Fatima. Not doable. Layan. Florence, not doable. Maisa, not doable. Majority. High accurate, doable, cost depending on the technology of the string used. Yeah, man. I think you will enjoy doing it on daily basis. We'll give you this task. Thank you. And in terms of cost, it's still cheap. Talking here about the cost of the tube and the small cup. Yeah, it is cheap because these materials are not expensive. So as you can see from this method, yeah, although it works, it also has some problems. It requires, it's not that accurate, slow, difficult to separate the oil layer exactly. You see some oil was left in the glass and some oil mixes with water during the transfer. Now I will take you to the last method of this challenge. Before I do that, I show you the measured amount of oil from this method is 40. Okay. Now I will take you to the final method. In the final method, we used a volumetric cup. In this method, I transferred the full contents of the cup to a volumetric measuring cup with clear markings that makes the readings of the volume easier. As you can see from this method, less mess, faster, no spill of oil. And what do you think about accuracy from this method? Do you think it's accurate? Accurate, yes, accurate. Majority agree that it is accurate. What about the doability? It should win as doability. I like this exercise. It's doable, yes, doable. Ryan, doable. Kifah, doable. Extremely accurate, very favorable, cost effective. Thank you, ma'am. Indeed. And in terms of cost, here we are talking about the cost of this volumetric cup compared to the previous ones. It's more costly, but it is giving accuracy higher, doability better. So although this method is fast, easy, not messy, we can say it's better than the previous methods, but still have some limitations. In this method, the reading depends on the eye level accuracy, and some oil sticks to the original glass. The measured amount of volume of oil from here is 50, which is exactly the same amount measured before the exercise. Here, this slide is a simple final assessment exercise for all the three methods. I thank you very much for your participation. You agree that some of these methods can give different answers for the amount of oil depending on their accuracy, applicability, and cost. Some methods are cheap but not accurate, while others are more accurate but might cost more. And this is exactly the mindset I want you to have before we dive into today's session on hydrocarbon saturation evaluation. As petrophysicists, our role is not just to calculate numbers, but to select methods that are fit for purpose, methods that are cost effective while still maximizing the business value. You will see this thinking clearly reflected in part 3 of today's session. The key message here is balance, choosing the right method that gives reliable results with affordable cost that supports the business decision. Imagine doing the same exercise underground in an oil and gas reservoirs where we cannot see or touch the fluids directly. Sorry. Where we try to figure out how much oil and gas are present in a reservoir and how to measure it accurately. The same winning conditions, the evaluation has to be doable, accurate, cost-effective, also guide us in real reservoir evaluation. In petroleum engineering terminology, when we talk about the amount of oil and gas stored in a rock, we express it as fluid saturation. And the process we use to determine it is called fluid saturation evaluation. Now, let's start with basic definitions that help you follow the session better. What is fluid saturation? Fluid saturation simply describes how much of the pore space in a reservoir rock is occupied by a fluid. The fluid can be water or hydrocarbon. The hydrocarbon can be in the form of oil or gas, or both. If we zoom in the pore scale of the reservoir rock, as shown here in this cartoon view, we see that the reservoir rock is composed of rock grains, this yellow, and pores, which are the voids or the spaces between the rock grains. In a petroleum reservoir rock, the pores are never empty, they are always filled with fluids. The pores can be filled with oil and water, or gas and water, or sometimes only water. In oil-water reservoir, the red here represents the oil in this cartoon, and the blue represents the water. When the oil occupies part of the pore space, we call it oil saturation in a gas water reservoir. The green here represents the gas and the blue for water. When the gas occupies part of the pore space, we call it gas saturation. And the percentage of the pore space filled with water is called water saturation. If the reservoir is occupied with oil or gas, it's called a hydrocarbon reservoir, which is our main target for production, and you will hear me using this terminology a lot, hydrocarbon, during the session. One important rule to remember: pores are never empty. So the sum of the hydrocarbon saturation and water saturation is always 100% or 1 in fractional form. That was the definition of the hydrocarbon saturation, and the code we use it normally is SH. So sorry, this slide should be hydrocarbon. The SH is represent the hydrocarbon, not the fluid saturation. The fluid saturation evaluation represents the determination method of the amount of oil, gas, and water present in the reservoir under in situ conditions. In situ means at reservoir conditions where we expect high temperature and pressure. If we now zoom out to the field level, we move from the pore scale to the entire reservoir. At this scale, we start talking about STOIIP. STOIIP stands for stock tank oil initially in place. It represents the total amount of oil present in a reservoir before any production. And GIIB is a similar term used for gas reservoirs. It's important to note that the STOIIP is a volume. It's expressed in barrels or cubic meters, while the hydrocarbon saturation, SH, is not a volume, it's a ratio, it's a percentage. The hydrocarbon saturation tells us how much of the pore space is filled with hydrocarbons. For example, if we say SH, the hydrocarbon saturation is 60%, it means 60% of the pores are filled with hydrocarbon, whether oil or gas, and 40% are filled with water. So this is the main difference between STOIIP and SH. To calculate the STOIIP, we use this formula, which is maybe familiar for most of you. And to calculate it, we need to add several input parameters: reservoir area, reservoir thickness, porosity, average hydrocarbon saturation, and formation volume factor. So the hydrocarbon saturation is one of the key inputs for STOIIP volume calculations. So keep this information with you. The hydrocarbon saturation tells us how full are the pores with the hydrocarbon saturation. It's a fraction. While the STOIIP tells us how much oil is there. It's telling us how much, the quantity. In today's session, I will not cover the STOIIP chip calculations. Our focus today will be on how to determine the hydrocarbon saturation SH. I hope this is very clear for you, these differences. Now, I will give you a chance to ask questions at the end of the session if there is no clarity about the definitions. I'm ready to move to the second topic of today's session. It is the reservoir's fill. I like to ask you questions. I like to know how you are thinking. I said earlier, the saturation is a fraction, it's a ratio. So let me ask you this question. In a hydrocarbon reservoir that has oil, why the water is always present in the reservoir? Why the hydrocarbon saturation is never 100%? This time I want to hear your answers. Don't write in the chat box. I want to know what's your understanding. Exactly. What is your discipline? Geologist? Yeah, that's great. That's a very good addition to the session. Exactly. So, to answer this question, we need to go back in time. Before oil migration into the reservoir, the rock was already deposited at different depositional environment, which could be seas, rivers, deltas, or lakes. This means that the water was already present from the beginning. Yeah, as our colleague mentioned. You see from this cartoon view, at the time of the deposition, all the pore spaces between the rock grains were completely filled with water. The blue here represent water. In petroleum engineering, we call this water connate water or formation water. Connate water is the water which is trapped in the rock pores at the time the rock was deposited. Connate is a Greek word, means bound together. So at that stage, the water saturation was 100%. All the pores were filled with water. As petrophysicists, we also care about formation water salinity, which is expressed in ppm or mg per liter. The salinity depends on the original depositional environment. For example, some PDO North fields have very saline water up to 250 ppm. I'm not sure if it is even more than this, because I didn't work for the North for a long time. Most of my experience in the South. While some fields have less saline, around 35,000 ppm. This differences becomes later on important for us as petrophysicists because it affects which saturation evaluation models we use and also affects our selection for logging tools. So to summarize, water was there first, and this slide partially answers our question, why is water always present in a hydrocarbon reservoir? We will need 2 more slides to complete the full answer. Why SH is never 100% in a hydrocarbon reservoir. Now, I know we are having some graduates joining this session, young professionals, so I will show you a video explaining how the oil is formed to be ready to migrate into the reservoir.
2 billion years ago, marine organisms like algae and microscopic animals and plants died and settled on the ocean floor. Beneath other sediments in the ocean, and in the absence of oxygen, These fossils changed into a substance called kerogen. Under heat and pressure, kerogen gradually changes into oil or gas. The whole process usually takes at least 1 million years. The constant pressure and movement of the Earth's crust squeezes oil and gas through the pores or spaces within rocks. Some oil and gas reaches the Earth's surface and seeps out naturally into land or water. Often it is trapped beneath the surface by impermeable layers or rock structures, like faults and folds. Within the crust, oil or gas deposits build up and form reservoirs. Reservoirs are like vast sponges filled with oil and gas. They can be as large as a city.
That was a very basic explanation how the oil is formed. After the oil is formed, it migrates to fill a wet reservoir rock. The red here represents the oil. During the migration process, the oil displaces the vulnerable formation water. This process is called primary drainage. I want to show you this video to help you understand how this happens, how the hydrocarbon migrates in the reservoir. This is a very simple illustration that will help you try to understand or visualize the process. At the beginning, sorry, I will try to reduce this. I want to explain while showing you the video. At the beginning, here, sand is mixed with the organic coconut oil, trying to form something like a source rock. In reality, be careful. The hydrocarbon is not a coconut oil. This is just an illustration or demonstration to see how the hydrocarbon at the solid phase. Now on the top, adding sand, which is the reservoir, preparing the layer for the oil to migrate, and then there is a mold. The mold here acts like a seal. It prevents the fluids from escaping. It's similar to the impermeable rock layer underground. This is the seal. When we apply high temperature to this system, the oil will turn to a more liquid phase and will start to move upward, as you watch from this video. And the oil movement happens naturally. It's a natural phenomena, you can see. This represents what happens in the reservoir, where high temperature and pressure allow the oil to migrate into a permeable reservoir. And the trap here prevents the fluids from escaping from the reservoir to accumulate in the reservoir. I want you to notice that the movement of the fluid is happening upwards and naturally. Now I want to explain how the pores are filled during the oil migration. This is influenced by the capillary forces that influences the vertical movement upwards, tending to fill the larger pore space faster. This video also will help you understand and visualize the process.
Hello, Mr. Gazda here. Today we will be looking at a demonstration on capillary action. So what we have here, I have 300 milliliters of water in each one of these beakers. I have these tubes, and I'm going to put different size sediment in it. Sand in one and small pebbles in the other. So on this side will be the smaller one. This is sand. This would be like typical East Coast beach sand. You've been at the beach anywhere in the East Coast, Massachusetts, New York, New Jersey. That's that type of sand. And then on the other side, I'm going to have this, which is basically like really small pebbles. So it's much larger size particles than the sand. So what I have is I have the 200 milliliters of each that I will put into these tubes right here. Okay, there we go. That's satisfying. Okay, so we have that. Now, what I will do is I'm going to basically place, so it's the same amount of water, same amount of sediment. I'll put that in there like that. And then I will put this in here the same way.
Watch how the water will rise up. Which one is faster?
And you can see the water rising up from the bottom. There's a screen on the bottom, which is actually an old piece of t-shirt that I cut, and we see it here as well. We want to see how high above the water line it rises.
This is the effect of the capillary forces. Also, it's a natural force. And you see the rock that have a better permeability, filling the pores faster.
This is to there. In the smaller sediment, this is smaller, this is larger. And the larger ones, notice it just went up to right there. If you can see it in the video, the line is right there, which is lower than here. So the smaller the sediment, the smaller the spaces are in between there, the higher up it will go. And let me maybe get a different view of it here. So you can see here, if you see the water level there, that's where the water, due to capillarity, moved upward. It did move up a little bit, but over here, you will see it's that much more. Maybe if I zoom out, you see them both. Yes, you can see that there, and then you can see it there.
During the oil migration, in this process, the rock larger pores are filled faster with the fluid because they require less entry pressure than the smaller, tighter pores. The oil in this process will continue filling the trap until it reaches its maximum storage capacity. After reaching to this stage, the fluids will be going through redistributed in the reservoir by the buoyancy forces and gravitational forces, which influences the segregation of the fluids types, gas, oil, and water. And we'll remind you also with this science.
Have you ever noticed that oil floats on top of water? It has to do with how water molecules interact with the oil molecules. Oil is insoluble in water. That means it doesn't dissolve in water. The way in which two substances interact depends on the molecules that make up the substances. When oil is poured into a glass of water, the water molecules and the oil molecules meet for the first time. As they are stirred together, the water molecules and oil molecules move around each other. When the stirring stops, the oil and water immediately begin to separate. This is because the oil molecules are not attracted to water molecules. They are more attracted to other oil molecules, and so the oil molecules clump together. At the same time, the water molecules also clump together. Water molecules are more attracted to each other than they are to the oil molecules. As the oil molecules and water molecules clump together, they separate. This is because oil is less dense than water. The oil molecules rise above and float on the water molecules.
As you can see, as you saw, the fluids, lighter fluids settle up, heavier fluids move down. And this also happens naturally. So, to summarize, when the oil migrates into the reservoir, it pushes out the movable water. Some water will remain trapped in the reservoir, which is this is the blue one. They are held by capillary forces, and this trapped water is called irreducible water. And its saturation, we call it irreducible water saturation. It's around 20 to 30% depending on the rock type. This water is held by capillary forces as well as by surface tension, and these are all Mother Nature forces. And the irreducible water is the main reason why the hydrocarbon saturation is never 100%. Once the migration is completed, the fluids will settle naturally, gas up, oil below, water at the bottom, forming clear fluid contacts. This is the final reservoir geometry, and this is what we use for well placement and field development. This slide summarizes the key saturation terms and how they are related to the reservoir life cycle. Connate water is the original water trapped in the rock during the deposition before the oil migration, when the water saturation was 100%. The irreducible water is the water that remains after the oil migration and cannot be displaced by oil. During the oil production, some oil still remains trapped in the pores. This is called remaining saturation of oil, RSO. And this is the recoverable hydrocarbon. And after water flooding or before planning any EOR, enhanced oil recovery, the oil that cannot be produced anymore is called residual oil. It cannot be recovered with normal recovery mechanisms and might require other advanced methods to recover it. Each term describes what remains in the pores at different stages of the reservoir life. Petroleum engineers use these terms in saturation, in evaluation and production discussions. I just try to explain it in very brief to let you have an overview about them, because myself I was confused about different terms and why they are called like that. From this slide, I want to affirm in brief, these saturation terms are not just technical definitions, they are used to derive the business decisions. The irreducible water tell us how much water will be always present in the reservoir, and therefore we can know how much oil we have on the ground. The remaining oil tell us how much oil is still available to produce during the life of the field. The residual oil tell us how much oil is left behind after normal recovery mechanisms like water flooding, and whether it's worth investing in EOR or not. Now I will take you to the last part of my session. It will be more technical, but inshallah we'll be able to catch what I want you to take from the session. Before I give you an overview about the saturation evaluation, it is useful to look briefly at the history of fluid saturation evaluation. In the past, logging tools were used mainly to identify the rock thickness that holds the hydrocarbon. It was used to identify the net sand, net pay, hydrocarbon type, and complete and produce the intervals based on this information. So the challenge they had before that they knew where was the hydrocarbon, but not how much oil and how much water were inside the pores. They don't have the volumes. This challenge was figured out by a scientist named Archie. This is his photo. I hope it's the real photo for him, who developed an equation to quantify the fluid saturation from the log responses. His equation is called Archie equation. It is this one. Archie equation allowed us to move from the qualitative interpretation into the quantitative interpretation. If you know the porosity of this zone is 30%, by using Archie, it became possible to know that some of it has 50% of gas and 70% of oil saturation. The porosity equation was developed first, then Archie later on used this porosity to quantify the fluid saturation. So we'll see the porosity is an input into the saturation evaluation. Archie used very basic physics that we all know, conductivity and resistivity. The conductivity means how easily the electricity can flow. The resistivity is the opposite, how much the material resists the electricity. I will show you this short video to see how the conductivity works in real life. If you forget this physics, you will remember it from this video. The aluminum is a conductor. It allows current flow. So he's testing the current flow using the aluminum. Yes. Now he will test it in a tap water. Now he will add salt to the water, and you will see how that will affect the conductivity of the water. The light will turn on. This is the conductivity effect after adding the salt to the water. So Archie used this concept to develop his equation, as will be explained in the coming slides. Now let me test your information about conductivity and resistance. Which one is more resistive to current? Write in the chat box. The dry rock, oil, salt water. Which one is more resistive to current? I will read your responses. Rock, Kawthar, yeah, oil, Mu'tasim. More responses. Rock. Nihal, Selma. More responses. Oil, Turkey. Both answers are correct. Salt is the only conductor that allows current flow because of the dissolved salts. This is This simple difference is the foundation of the resistivity laws and Archie equation, as you will see from the coming slides. Now let's repeat the same quiz for our reservoir system. A reservoir with oil, rock grains and formation water. Write your response in the chat box. Which one is more resistive to current? It is the rock, grains, the oil, the formation water. For this reservoir system, which one is more resistive to current? Oil, 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 yeah. Excellent. You have to teach petrophysics, mashallah. Correct. Yeah, and we can see this from the log response. Thank you for your responses. Khulud, great. Oil and grains. So the electrical current flows through the connected saline water, not through rock or hydrocarbon. Because Khulud is a petrophysicist, that's why she mentioned both. Now I will explain little bit some information about Archie. Archie developed this equation, this one, through laboratory experiments, but the details are too technical for today's session. So what really matters, that Archie identified a simple link between the rock porosity, the formation water, and the electrical behaviors of rock and fluids to estimate the hydrocarbon saturation. In Archie model, it's important to note that it assumed that the conductivity comes only from the formation water, and the rock and oil, which is the hydrocarbon, are not conductive, and the salinity of the formation water is constant. If we introduce another conductive material to this system, the relationship will break. So that's why in shaly sands, the clay minerals conducts electricity, and Archie no longer works, and that's why we use Waxman-Smith equation, which is a similar version of the Archie, adding the correction for the conductivity from the clay. Here, I have another question for you. For those who can read the logs, who know how to read these logs, I want you to tell me from this interval, it is called Mesozoic clastics, regardless of the name of the zone. What is the oil contact? Where is the oil-water contact here? Can you write your estimate for the depth? Where do you think is the oil-water contact for only this interval? Write it in the chat box. The oil-water contact, 824. Yeah. Al-Mu'tasim, yes. Other responses? For this interval, where is the oil-water contact? Eight to four. Safe. Any more responses? Why the PP is in the silent mode? You should know it. 820. Khulud? Yes. What else? Kawthar, 820. 820. Miro, 820. Yeah. 820, 824. Here is the answer. The top part is not, the high resistivity in the top part is coming from the tightness of the rock. And this is showing you one of the limitations for using the resistivity to quantify the hydrocarbon saturation. In tight sand with very low porosity, it can give high resistivity, but this resistivity is caused by the rock, not by the hydrocarbons. PPs can clearly note these responses with very high resistivities. Now that we understand the physics behind Archie, let's look what meaning of the Archie equation parameters. We PPs, when we study the reservoir rock, we study it at different scales. When we explain Archie, we are actually talking about thin sands and microscopic images. At this scale, we clearly see the rock grains, the pore spaces, and the fluids filling those pores. Now I will explain the parameters that form Archie equation. SW is the water saturation. Once we know SW, converting it to hydrocarbon saturation is very easy because the pores are never empty. Water saturation plus hydrocarbon saturation equals 1. So the hydrocarbon saturation can be determined by subtracting 1 from the water saturation derived by Archie. The porosity tells us how much of the pore space exists in the rock, which most of you should know it, and the deep resistivity, how hard it's for the electricity to pass through the rock fluid system. Both of these logs, the porosity and the deep resistivity, are measured from the logging tools. The RW is the formation water salinity, and that's why it is important. If we are using Archie, the salinity of the formation has to be constant. This is reflecting the salinity of the formation water. M and N are parameters that sometimes are assumed if we don't have them, or derived from core. The cementation exponent represents how the pore networks are connected together, and the N represents how easy the water connects the electricity. So it is all about electrical behaviors between the rock and the fluids. And the A is the torosity factor. And most cases we don't have these parameters, we use assumed parameters. And sometimes we can measure them, but to measure them we need to do some of other workflows. Because I'm talking to non-petrophysicists, I don't want to go to the details of all these parameters derivations. Now I will take you to the BDO saturation evaluation methods from logs and core. This slide explains the evaluation process by any PP in BDO. The process starts with planning by proper selection of evaluation techniques and logging techniques. Then perform safe logging operations. After that, petrophysicists quality check the data and do analysis to finally share the results for business decisions. The best method selection should meet the same criteria. The methods has to be accurate, cost affordable, and doable. In PDO, The interpretation is for hydrocarbon saturations is done based on gathered data from logging devices. We run them in open or cast hole, or from lab core analysis. Logging, the term means lowering some electrical sensors in a well to record data. Coring, the term is used to explain the operation of cutting a rock sample from a drilled well. Coring analysis is an experimental evaluation for small rock samples, and they are classified into conventional core analysis, CCA, or routine core analysis, they are representing the same, and special core analysis, SCAN. The hydrocarbon saturation can be evaluated from both, from logging and from coring. I will explain now how we get the log data very quickly. We drill a well that penetrates the reservoir target to be able to acquire the logging data. The well trajectories depend on the best development options for the field and depends also on the location of the target reservoir. Then logging tools are used to gather the required data. We are having multiple of sensors for different objectives, and here is the role of how the brain of the PP can digest all these types of tools and know where to use them and when. Because some sensors can be used only for open hole and some can be used only for cast hole. So depending on the requirements and tool limitations, the petrophysicist can select the best to meet the requirements. As I mentioned, the logging tool selection is based on tool physics, position. Just imagine the petrophysicist has to know all these details, limitations, the physics, and to maximize the value from these logs. And the methods for recording the data is also, we are having different methods. The most common methods we use for open hole logging is the wireline or the LWD, and the methods vary in cost. Also for cast hole we are using different methods. The most common method also for cast hole is the wireline or the tractor, and we run the more advanced technologies, which is very costly depending on the value of information we need from the data. After getting the data, the petrophysicist will QC the data, analyze it in a software, we call it TechLog. This is just for the basic interpretation. Not all the data can be processed or analyzed in TechLog. And this PP analysis data is used to generate what we call it is RDL. RDL, Reservoir Data Log. It is a record of open hole log data and the evaluation results. And you can see from this display, the SH is one of the key outputs in the petrophysical evaluation. We read the scale for the saturation from 0 to 1. Personally, I like to color it using color code. Saturation red when it is more than 50% and orange when it is less than 50% for easily visualization for non-PPs. We use the evaluation results at the end to complete and produce the oil and the hydrocarbon. Here is a summary of BDO hydrocarbon saturation evaluation methods that I know. There might be other methods that I am not aware about it. The most common methods is the salinity contrast logging tools using the resistivity. And as I explained in today's session, we are using Archie to evaluate the hydrocarbon saturation for clean sands. For shaly sands, we use Waxman-Smith. There are other saturation advanced models or logging techniques that were developed based on the physics of different technologies, reservoir complexities, and the business requirements. When it's not possible to use the salinity contrast physics, we use other technologies like NMR, RST, electrical behaviors to evaluate the hydrocarbon saturation. And there are advanced modules used for thin bed reservoir analysis, complex lithology, and low resistivity pay, which is not, I'm not very familiar about it, but I have done some of in the past. From core, the hydrocarbon saturation is evaluated using Dean-Stark analysis and capillary pressure. As you see, there is a variation in cost of some of these methods, and we decide to select more advanced technologies that will require us to cost after doing value of information. The value of information answers one key question: is this information worth we need to acquire it before making the decision? Will it tell us or help us to reduce the uncertainty or improve the confidence? And can it help us to change our decision or rank the decision options? And will the value from the information gained will be greater than the cost we spent to get this data? So I want to show you some cases that will show you from video case that will tell you not always we should avoid the cost effect methods, because sometimes it can give us very key information that can close a very big uncertainty gap. Here I have a case. What the log is telling us that MG2 unit is not having attractive hydrocarbon. This is what the log tells us. But what the core is telling us that this unit is dominated by shale interbedding sands, and this shale is masking the resistivity measurement, causing it to underestimate the hydrocarbon saturation. And this orange is the measured hydrocarbon saturation from Dean-Stark, from core. So this case showing that not always high cost should be avoided, because it can help us to close a big uncertainty gap and open opportunities for developing some of these reservoirs. I have here another case. In this case, it's showing the value of using advanced technologies like NMR, RST, which is salinity independent. In terms of cost, it is more expensive than the normal approach from the resistivity, but it can help to close a very big uncertainty in evaluation saturation. In this case, injected water was used to enhance the production from the field. And what they used for injection formation water produced from the reservoirs and fresh water from a surface unit. This injection of the mixed salinity affected the hydrocarbon saturation evaluation by Archie, because the resistivity was reading high resistivity, thinking it is a hydrocarbon while it's not. After running salinity independent technologies, RST found that this interval is actually water, and the resistivity was affected by the injected fresh water. And this also was proved by collecting downhole samples from the high saturation zones, which showed that it is having some water. Yeah. Now, finally, I would like to conclude by saying that today I explained just one topic in the PP world, I tried to simplify it as much as I could. And I hope that you didn't lose your attention to the topic, and I hope I was successful to make it an interesting topic for non-PPs. When we look at the rock with the PPIs, we see pores, grains, fluids, interactions at small scale. For the PP, the rock is not just a rock, it's a lot of information that is useful for the gas and oil industry sector. With this, I conclude my session, and I will give you the floor to add to the session if you have want to add any more information to it, and I can give you a chance to ask your question.